My name is Frank McKenna. I work at UC Berkeley. I'm sponsored by Pierre and the National Earthquake Engineering, Denise, Georgie Brown Network for Earthquake Engineering. So the motivation why I think it's important that we actually have this webinar is if you consider if your desktop represented the computational resources available for you today to actually perform large simulations, then I would argue that if you only used your desktop to perform these simulations, it's like doing the simulations using your fingers. There's just so much computational resources out there that as structural engineers you have to start using, particularly those in research, you graduate students doing your research in performance-based earthquake engineering. So the outline of today's talk, basically I'm going to a brief overview of how technology is changing. I'm going to then go into about OpenSees for parallel and grid computing. And finally I'm going to show you how it's done. Parallel and grid computing is actually done on NESHub. So first, building blocks for simulation. Typically as engineers, when you're looking at a simulation software, all you care about are the elements and materials that make up your model. Finite element applications, they're built using many more components than just the elements and material types. There's also sort of numerical computation, algorithms and solvers, and also how you visualize the data, how the data is stored. There's just an awful lot of stuff. And all this stuff, this bridge, it rests on hardware. And that hardware in the last 10 years is undergoing dramatic changes, dramatic shifts. The finite element method as you know it has to radically change. It has to evolve into something different. If we continue doing the same stuff, basic finite element analysis, using the same algorithms and the same solvers as we're using now, in 5 years we'll be a laughingstock among all engineering disciplines. We have to change. And the reason we have to change is hardware is changing dramatically. It's changed incredibly in the last 10 years. Some of this is due to the fact that basically the chips on which our computers are based have changed in the last 5 to 10 years. They're no longer single core machines where you run sequential processes. Now any computer you buy since 2006 has multiple cores in it. There are multiple processing units on every chip. The desktop I have has 8 cores. The little laptop in which I'm doing this presentation itself, it has 2 cores. And it's actually a pretty old laptop I'm using. So the processor speed, with the addition of these cores, it's keeping up. It's keeping up with Moore's law. We're continuing to double the performance every year and a half or so, and that's only because we're adding more chips or adding more cores to the chips. We're adding more processing units to the chips. But these speeds are pretty pathetic when we look at, for example, the game consoles. You know, my child has a Sony. It is 5 times more powerful than the fastest desktop server I could buy right now. So we're using machines for doing our numerical computation that are pretty much almost outdated. What we could, if we wanted to do, was I could right now go out and buy a graphical processing unit, attach it to my desktop computer, and the floating point operator, the performance that I could obtain if my software allowed it would be approximately 4 times faster for doing just pure matrix algebra than my current processing unit. So as I say, we have to change, and that GPU, it's going to change. In the next couple of years, Intel and NVIDIA, they're having a little war. Intel's going to be putting GPUs on the motherboard as part of that chip. NVIDIA is coming up with processors that they'll be as powerful as regular CPUs, but they will in addition have GPUs on the board. So things are changing, and we have to start rewriting our software to take account of these changes. So basically, everything we do in the future will be we'll be using parallel computers to do it. A parallel computer is a collection of processing elements that cooperate to solve large problems fast, or at least faster than they can be done on a single processing unit. So here's a little picture of what a parallel computer looks like. Basically, there's some processing units which are able to communicate amongst each other. They share memory and they share a file system. These processing units can be the CPUs that we're typically used to, or they could also be the graphical processing units I mentioned. So where are we going with parallel computers? An interesting site is the top500.org. It has sort of monitored the fastest 500 computers in the world for the last 15 to 20 years. Every 6 months it updates its list. And what this graphic here shows is basically the green line in the middle that's going up is the fastest computer in the world. Currently it's about 10.5 petaflops per second. It also shows you the 500th fastest computer in the world, which is currently at 51 teraflops per second. And by 2019 or so, we expect to hit the 1 exaflops per second for the fastest computer. But just the interesting thing about this slide is it shows how long it takes for the computers to remain to remain in the top 500. Basically, the fastest computer will only stay in the top 500 for about 6 to 8 years. We ourselves will get a computer as fast as the slowest computer in the top 500. It takes about 8 to 10 years. So in about 15 to 20 years from now, I will have a computer that's as fast as the fastest computer in the world right now. The thing about these fast computers is they have an awful lot of processing units. The little slide there is showing sort of how many processors are how the processor count has been changing over the years since 2000. Basically, the fastest computer right now is over 250,000 cores or processing units. Now that sounds like a lot, and it sounds like we're going to greatly improve the performance of our applications. But there's a little problem we're encountering. So when we go to parallel machines, what we want is speedup. We want our applications to run faster on the parallel machine than if they were running sequentially. The definition of speedup is basically the time it takes to run on one processor versus the time it takes to run on P processors. Now what Amdahl did is he broke this up. He broke up speedup into its components, basically the proportion of the job that runs sequentially, which is alpha. So he comes up with this little relationship where speedup is dependent on the T1, the proportion of T1 that has to remain sequential, and then the rest of that, the job can be split up perfectly, run in parallel. And he came up with this simple relationship, which is the number of processor goes to infinity. A speedup is just 1 over alpha, alpha being the proportion that has to run sequentially. And he came up with, then you could plot this, if you plot this little relationship for different values of alpha, which I've done here, what we would like is linear speedup, i.e. if we throw twice as many processors at the job, our job is going to run twice as fast. And this graph shows that, it's how fast the job will run in parallel really depends on how little of it will be sequential. For example, if I can only find, if 10% of the job has to be done sequentially, there's nothing I can do about it. For example, I'm building my model, or I'm actually solving the equations, the AX equals B equations. There's a portion of that just has to be done sequentially. And if that portion is, say, 10% of the problem, the maximum speedup that I'm going to achieve will be a factor of 10. So even though I have 200,000 or 300,000 cores available to me, the maximum speedup I can actually achieve is 10. So we're greatly wasting, or will greatly waste all the processors available to us unless we start changing our algorithms. And the thing is, sort of what I'm showing here in this slide from Jim Demmel, who teaches parallel programming here at Berkeley. is that this gap, now typically the typical application running on a parallel computer is only able to make use of 5 to 10% of the processing power of the computer. That's say with the 200,000 cores. In the next 10 years, when we go to when we hit the exaflop barrier, like 2019 or so, that machine they predict will have somewhere between 10 and 100 million processors. And unless, again, unless applications change in general, the usage, instead of going to 5 to 10%, we'll be lucky if we're able to achieve 1% of the efficiency of that computer. So we'll be, greatly wasting the resources if we don't change. So in a lot of computer science disciplines and numerical algorithms, they're looking at new algorithms to achieve higher performance. And what we're going to have to do is we're going to have to change our methods to take account of these new algorithms. And Amdahl's law is quite simple. It actually ignores data, and data is becoming an even greater bottleneck to speed up. Data movement between the processing units is very expensive. In comparison, flops are incredibly cheap. So what this means is that we're going to have to start looking at different algorithms within our applications. For example, in finite element analysis, we're going to have to start looking towards using iterative solvers instead of direct solvers to solve our equations. We're going to have to look at, say, using mixed precision arithmetic. Like, we don't need double precision arithmetic typically. We can get away with single precision arithmetic. Or if we do need the double precision arithmetic, we could be solving AX equals B in single precision and then using iterative techniques to improve it if we kept the matrix in double precision. And also we'll be doing sort of duplicate calculations, which I'll talk about later in the presentation. Okay, the thing is, it's not just high-performance parallel computers that we have to concentrate on. As I say, your desktop computer is now a parallel machine. And also we've got something called grid computing, which is, an incredibly powerful resource that we have available to us. Grid computing is basically the most distributed form of parallel computing. Basically, the computers are communicating over the internet. They're not in one single room with a high-speed switch between them. Basically, I can have a computer here talking to, say, something in Italy. These grid computers are characterized by incredibly low bandwidth and high latency for sending data across. But they can be useful, and I'm using them at present for doing some, I'll show you what I'm using them for later. But here's an example of somebody who's using OpenSees and the Open Science Grid, which is basically one of these grid computers. What they want to do is basically do some parameter studies. And what the fellow did was he had I forget how many hundreds of analysis he had to do, but he's able to do all his analysis on 30 days. And he calculated if he was just running it on his desktop sequentially, it would have taken him 12 years to finish. So he saved himself. He was able to actually do his work, actually get his research done in the 3 years that that PhD requires. PhD students, they can't be spending 12 years to wait for their simulation data to be done. They need it now. They need it, as I say, within the 30 days here. So that brings us to cloud computing. So this is basically work that the stuff in this slide was presented by Steve Jobs back in 2011. And at the time, he was saying that everybody considers sort of this is the hierarchy for their computing. Basically, you've got the desktop, and beneath the desktop, you have your phone and your iPad. What Steve pointed out was, this is no longer true. Your PC or your Mac, they're just now typical little devices. You don't typically do any more computation on your desktop devices. The desktop devices, all your work will be done in the cloud. As you pointed out, some people think that the cloud is just a hard drive in the sky, is somewhere to store your photos, somewhere to store your Word documents, and for syncing between your different applications or your different computers. It's actually not that. Cloud computing is internet-based computing whereby the shared resources, software, and information are provided. The important thing is it's providing on demand. Anytime you want something, anytime you want, say, to access a parallel computer, you can just log in and start running your job on a parallel computer. If you need 100,000 computers or 10,000 desktops or however much computing power you need, you can go get it on demand. And the resources that these are the sort of the high-performance computers, grid computing. It's also large storage areas. We have terabytes and terabytes of storage out there that you're allowed to use at any, if you need new hard drives or whatever, you can just go out now to the cloud. You can go out to places like Amazon to go get your things. So industry users there's a number of systems out there that allow people to do cloud computing. We have Amazon Web Services. Windows offers a service, and so does IBM. Currently, I'm using Amazon Web Services quite a lot. If I need a Virgin computer that only has a certain operating system on it, I'll go to Amazon and find that particular setup. If I need a Windows machine, for example, Amazon, I can get a Windows image. It's just like a Virgin machine with nothing on it. So I can go off and build OpenSees for somebody and give them the instructions on how to do it. But also for us in earthquake engineering, we have the NEAS Hub. It's basically resources that NEAS makes available to us. They have storage and also computational resources for parallel computing. And at the end of my presentation, I will demonstrate some of the resources that NEAS Hub has made available. So that's the end of where we are with technology. So now I'm going to jump into basically the parallel aspects of OpenSees that not many people know about or use. So when I started OpenSees, back when I was doing my dissertation, it was not to do finite element analysis. What I wanted to do was basically, my research was into parallel computing and how to do load balancing. So OpenSees has always been set up to build applications for both sequential and parallel environments. And there's nothing much importance on this slide, just to show you the original setup in the class hierarchy, that everything was always a movable object in OpenSees. So if you're a code developer and you want your new code to run in parallel with the rest of OpenSees, there are basically two methods that you have to implement: the send self and the receive self object methods. With that, your code will run in parallel. And again, if you're doing an new analysis class, a new integrator, a solution algorithm, or a system of equation, again, your object will subclass off the movable object. And if you want it to run in parallel, again, you have to implement the send self and the receive self methods. And we've also methods in here just basically for domain decomposition and substructuring, which I'm not going to talk about. But under the covers, when you actually do some domain decomposition in OpenSees, these are the classes that are actually being used. So now I'm going to go back to basically the interpreters, which is how most people use OpenSees. They don't create their new applications using C++. They write their scripts. For parallel processing, we provide two parallel interpreters, OpenSees SP and OpenSeesMP. OpenSees SP is an application for basically large models in which we don't want you to change your script too much. You basically take your script that will run sequentially, you make one modification, and it will run in parallel. So what the script does is as I'll show you in a minute, it basically does some domain decomposition. The element state determination is done in parallel, and some of the equation solving is also done in parallel. Now OpenSeesMP is the other application. It is built for both large models and also for doing parameter studies. It is by far the most widely used of my parallel applications. Most of the graduate students doing performance-based earthquake engineering within PEER are using OpenSeesMP to do their parameter studies when they're running on parallel machines. I'm going to talk about both these applications in a little more detail now. So to say OpenSees SP is for large models. And what OpenSees SP is basically it's your typical interpreter, and it's just sitting on one process. The other processes in the computation are sitting there doing nothing. They're just waiting for something to happen. So what we do is when we build the model, as I say, everything is built on P0. That's where the interpreter is. So when you add new elements or add materials or you construct your analysis, everything is built onto P0. The other processes are sitting there waiting for something to do. And it's only when the interpreter comes across the analyze command that it actually does something. It does a process what's called domain decomposition, which basically splits the elements, nodes, and load patterns and loads up into different partitions. And the process will then send out to the different processes in the computation different elements and nodes. So after the domain decomposition has taken place, some parts of the model will be scattered on different processes all over the place. And then as it does solve the AX equals B, that computation, that solving the AX equals B, is done in parallel for large portions of the, as much of that is done in parallel as possible. And we'll talk about sort of the performance here now. So here's an example usage. This is the largest sort of non-made-up model we have. I'll show you later larger models. But this one is actually it was a model of a building that was done as one of the within PEER for studying the Humboldt Bay Bridge. And it's by continuum models. It's a small model. It's only 100,000 degrees of freedom. The model was solved using implicit integration for the time transient analysis, and we're using the MUMPS direct solver. And I'm showing here the sort of the performance improvements that were obtained. The student, it was taking about 6 hours or so to run on a single process. When we moved it up to 16 processes, we were able to get it down to under an hour. So it's a six-fold increase in performance using 16 processors. And the shape of that graph is very typical of what's going to happen when you're using an implicit integration scheme in a direct solver. Somewhere between 8 and 32 processes, you're going to bottom out on the performance improvement. As you start throwing more processes at the job, the performance is actually going to get worse. So there's a happy point that you reach, and it's typically, as I say, between 8 and 32 processors. And this is typical, again, for a direct solver. And the problem is basically the communication required. At some point, we just hit a barrier. Some of this computation has to be done sequentially when you're solving AX equals B, when you're using a direct solver. So we can't improve the performance any. But if we were to change again, as I mentioned, we're going to have to start changing what we do. Here's an example of a student. This was a totally made-up problem where he went as high as 73 million degrees of freedom. And he found that he could scale perfectly if he just used a different solver and integration scheme. In this case, he's using an explicit integration scheme, the central difference method. And he's using, for the central difference method, he's able then to use a direct solver. So basically, the matrix is a diagonal matrix. So that scales beautifully. There's no communication required. And as I say, he's able to achieve perfect speedup just by changing his solver and changing the integration scheme. So it's something we're going to have to start looking at. So the other application, OpenSeesMP, Again, this is for both large models and parameter studies. So what OpenSeesMP is basically we have an interpreter running on every single process. And that interpreter is able to determine basically a unique process ID and also the total number of processes that are in the communication. And based on that information, it's able to do stuff. Okay? So there are some additional commands that are added to OpenSees to get this information. For example, the get NP and the get PID basically return the number of processes and that unique process ID. In addition, the processes are able to send messages between processes. I'm able to send a message from one processor to another during the computation. There's an additional method there called barrier. So every process, when it hits barrier, will stop until all the processes reach that point in the computation. And one other method that's in there is called domain change. It's an important command that's been added for when you're doing these large models in parallel, and I'll show you its usage in a couple of minutes. So here's a simple example, a tickle script. You've probably all seen these tickle scripts. But in this script, I'm actually using these new commands, the get PID, the get NP, sending and receiving messages, barrier. So what this script does, I won't go into too much detail, is initially every processor is going to send a message to P0. And initially P0 will loop over all the processes in the communication and receive the message. In that first loop, it doesn't care what the order is. It'll just receive a message from any processor. Then it's going to hit a barrier. And then in the second loop, it's going to receive them in order. Process 1 is going to go before process 2, before process 3. So when I run it, I see that. If I was to run it again, I would see a different set of numbers initially. Like those random numbers are going to change every time I run it. But the ordered numbers, hello from 1, 2, 3, 4, they will always be in that order. So here's another example. This was done within PEER when they were doing the earthquake evaluation, how to scale earthquakes. So what this is a steel building. The student came to me with this script. He wanted to run 7,200 records. Each record was taking 2 minutes. It would have basically taken 10 days to run. So we ran it on a 2,000 processor machine in less than 15 minutes. And the only things I did differently to his script was I basically added 6 lines of code. Those 6 lines of code are in red. Pretty much any graduate student who's using OpenSeesMP to parameter studies has those 6 lines of code in it. They haven't changed the variable names. They've kept them identical. So I know that everybody's basically seeing this slide or the next slide and using that to make the modification. So anybody can take their script that's doing parameter studies, modify it with those 6 lines of code, and it will run in parallel. Here's another example. This is a Berkeley student. She's a concrete building study. She had a little over 400 records, but it would have taken her 2 months to do all the analysis required. We were able to run it again in 5 hours on a machine. And basically, again, the only thing I did was I added those 6 lines in red for the parallel processing. And that's the only change we made to her script to get it to run in parallel. So when you're not doing parameter studies, you want to do large models, you can't use the commands that you're used to. Basically, you've got to specify that you're building a large model and it's going to be run in parallel. So when you want to do the degree of freedom numbering, you have to choose one of the parallel numbers. It's either parallel plane or parallel reverse cutting McKee. You have to use a parallel equation solver. In this case, I'm using MUMPS. In addition, if you're doing displacement control, you have to use the parallel displacement control instead of the normal displacement control. The arguments are the same, but you just have to throw the parallel in there, parallel displacement control. And again, this is only if you're doing a parallel model. Don't use these commands if you want to do the parameter studies, as they will mess up the computation and God knows what you will get out. So here's an example of a parallel model. Simplest example I could think of. For those of you who've been to the OpenSees Days workshop, this is the example I usually start with. So in this example, what I'm going to do is I'm going to put element 1 onto process 0, and I'm going to put elements 2 and 3 onto processor 1. So basically, again, I start off, I get my PID and I get my NP. If the number of processors are not equal to 2, I exit, because if I don't exit, this program will fail, the script will fail. So if I'm processor 0, I put nodes 1 and 4, and element 1 on process 0, and I also put the load at node 4 in the load pattern. That goes into process 0. And on process 1, I put the other nodes and the two other elements. The important thing to note from this example is that I do not redefine the load pattern. If I redefine the load pattern, what would happen in the analysis, I would get double the displacements, because I'd have basically applied a load of 200 in the x direction and negative 100 in the y direction to the model. So because that node 4 is on both processors, the important thing is you only apply the load once, you do not apply it twice, otherwise it's counted twice. So here's the parallel analysis part. Again, I told you we had to basically change the number and the system from a sequential objects to parallel objects. So I'm using parallel plane for my number and mumps for my system. So when I run it, this is example 4 in the materials that are available. This is what happens. So here's basically where I'm doing displacement control. Again, the integrator has to change from displacement control to parallel displacement control. And we also, for displacement control, we have to throw in a domain change. That's what it's used for. So anytime you're doing a large model on NP and you want to use displacement control, you have to use both the domain change method and you have to change your integrator. So parallel computing is fabulous, but it brings a whole bunch of little things you've never seen before into the mix. Some things that can happen are what's called deadlock. Basically, your program will hang. You'll start it, it'll start running, and it won't stop. It won't end until either you kill it or the system administrator kills your job. That's typically due to this mismatched send and receive messages or opening files. I'll go through little examples in a minute. The second big problem that can happen when you're doing parallel processing is what's called race conditions. Every time you run the application, you get a different answer, which is probably not something you will want to see when you're doing your analysis of your structure. You don't want to be getting a different answer every time you run the analysis. And finally, something else to watch for is load imbalance. Basically, some processors are doing a lot more work than others, so you're wasting a lot of the resources. That is something we don't want. So deadlock typically occurs, basically, the send and receives are not matched. So here's an example. It's back to that simple example I had. The only difference between this one and the example 2 is I've commented out the barrier command. So again, they're going to start reading them in randomly, and then P0 is going to start looking for ordered messages. So here's what happens when I run it. As I say, I'm going to get a different answer every time I run it. Sometimes it might work. So random messages are coming in from 2, 5, 2, 5, 3, 4, 6, 3, and 4. And then P0 is looking for the ordered messages. So he gets a message from 1, and now he's going to wait for a message from 2. But if you look in that random screen just above, 2 has already sent his second message. So 1 is just going to process 0 is just going to be sitting here spinning forever until either I kill the job or the system administrator kills the job. And that's an example of deadlock. Race conditions, basically, if there's a bug in the program, you'll get different answers. And it can also, if you're doing it in the script yourself, if you're reading and writing to files, that's the typical cause of a race condition, where you need to read information from a file and put it there when you're done. So that's the thing to watch out for, is just how you open the files. You typically want to open it with an R+, but you can look at the manual to see what that does. And the other thing you need to look out for is load imbalance, basically where some processes are working more than others. And I'll show you an example of how we fix load imbalance. So again, typically the students don't care too much about load imbalance, so they take their script and they run it. So there's basically the 6 lines of code again. So if I run this script, some records are different from others. It takes some longer to process than others. Here's what I got. Basically, processor 0 was done in 14 seconds. Process 1 was done in 6 seconds. So overall, it took me 14 seconds to finish. But processor 6, processor 1 could have been doing more stuff. It's only taking the 6 seconds there to finish, versus the 14 for P0. So what I did is I modified the script a little. Basically, I'm going to throw away a process that's just going to coordinate the workers. Basically, what's going to happen is he's going to ask for work. So when he's done, he's going to go back to P0 and tell him to give me more work. Okay, so that's a kind of a worker coordinator approach. There's other simple load balancing techniques that you can implement in your scripts, but this is the script for basically the worker coordinator. And here's when I do this one, here's the results. So processor 0, he's gone from 14 seconds down to 9 seconds. And processor 1, he's gone from 6 seconds up to 10. But overall, I've improved my performance. I've gone from 14 seconds, say, down to 10 seconds. This could be 14 hours down to 10 hours, 14 days down to 10 days. So it's very important, if you've got a big mismatch of sort of the time it takes to do the simulations, to consider actually implementing load balance into your algorithm, into your scripts. So the final part of my talk is I'm going to be talking about the OpenSeesLab tool that's available on NISHub. Again, NISHub is this fantastic resource we have available to us for cloud computing. NISHub makes available to us large sort of data storage repositories, and also it provides us access to some pretty impressive computational resources. Within the next couple of weeks, we're going to have access to a 60,000 processor machine that's ranked in the top 15 of the top 500 list. So OpenSeesLab, it's basically a tool for submitting script to the OpenSees Hub resources. And it was also intended to both educate students and practicing engineers on, things that they need to know. So the most basic thing it does is it allows you to run your scripts sequentially. There's a number of tools within OpenSeesLab. The first tool is the OpenSees interpreter. You run it like you're running your normal interpreter on your desktop. The nice thing about this is I can have multiple what are called sessions running. Basically, it's like having multiple desktops available to you. So you could be using multiple resources at one time if you just want to do these things sequentially. And another incredibly nice feature that the students are finding out is that if they have problems with their script, they're able to actually share the session with me. They do not have to send me an email saying that, there's a problem in my model, can you go find it? They can run it. If it doesn't work, there's a little button at the bottom, I'll show you in a couple of minutes where it is, where you can actually share the session with me, and that will allow me to see what you're seeing. I can You can watch me as I sort of look into the problem and see how I sort it out. So it just saves the back and forth emails between us. As I say, it's also for educating students. This is a simple example for lateral pile analysis. You can make this really simple interface. It's got OpenSees at the back end, the pile properties and soil properties. When you hit simulate, you get it. You can go back and change something. And then it allows you to compare what's the difference, say, between a pin-headed, fixed-headed thing. But these are, pretty educational. Now for this talk, there's a parallel script submission tool. This tool is being worked on right now. It's available to you to use. There's a number of parallel machine options you have. But this big one with the 60,000 processors will hopefully be with you in the next 2 weeks before I go on my summer vacation. The resource for that will be Ranger. It's not available right now. The Kraken resource that I'm showing right here, that's actually, we had to take that off. It might still be on what's on the NESUB when you start the OpenSeesLab tool. Again, if you use it, it's not going to work. We've basically used all the allocation that was made available to us on Kraken. So now they've got us another resource, which is called Ranger. They have a lot more time to give out on Ranger than they did on Kraken. So we'll be able to use it. And when you're using this script, all you specify is where the main script is, which machine you want to run it on, which application, whether you want to use OpenSeesMP or OpenSees SP, and then finally the number of processors you want. Again, I'll show you this in a couple of minutes when I run it. This tool I'm not going to talk about now. I'm kind of running out of time. It's another tool for doing parameter studies. There are examples of it. If anybody's really interested, you basically, in this one, you don't make any modifications to your script, and it runs. So I can talk to people who are interested later or offline. What I really want to get to is something that again is available on NESUB. It's allowing people to do what are called workflows, where it'll do sort of multiple applications, like everything OpenSees cannot do at all. A lot of you are using MATLAB and OpenSees and MATLAB to do stuff. This is an example of something that you could use to automate that process, because you're probably doing the same thing with just different files every time. So what a workflow does is it allows you to build a template of what the work is going to do. And then once you've built the template, you can repeat it multiple times, basically, for different input files. So in this little example here, there's 15 tasks that need to be done. Tasks 1 to 4, start off running, there's individual applications. They produce some output, which goes to processes 5 through 8. 5 through 8, again, they run independently. When they're done, they send all the information, then goes to, is basically the input for process number 9. When process 9 is done, it's got some output. That again goes to 3 different processes, 3 different applications, 10 through 12. And then when they're done, the results are again going to processes. Those results are inputs into processes 13 through 15. So what workflow software does is it takes a description of the work that needs to be done, and it handles it all for you. You provide a description of what the workflow looks like, and it does the mapping between that description and the actual where the stuff is going to happen. So when you start it running, it's going to take the different input files, it's going to take the applications, and it's just start sending it and putting it on different machines and doing the stuff. Now I have a tool that's finished development. We're just waiting for it to be released now on NESUB. Again, I'll show it to you. It's intended for research, for education of engineers as to, what can happen if you start considering the variability in the material properties. Which, you typically steel is not, the E is 29,000. It varies within an element and across elements. So we don't take that into account in our thing. But this tool is also there to provide you with how do you actually run Rapture, or how do you run Pegasus on the hub. You can download the source code to see what changes you need to make for you to create your own workflows. So as I say, this thing just does, if you just run one simulation, you get, say, what the results of if I've used, say, the mean for E and the mean for Fy and the mean for the hardening ratio, and those are the results for, I think it's 8 different earthquakes I have there. If I run it for, say, 10 simulations where the E, Fy, and the hardening ratio vary based on a log normal distribution for every element within the model, it's not just the same E is used within every model, but within every element E is changing. So that's what happens if I run it, say, 10 times. As you see, there's a big, I'm just plotting the roof displacement here. There's a big change in what the possible outcome might be. If I did it 100 times, so that's the distribution of what the roof displacement might actually look like. 1,000 times. So that pretty much concludes my presentation. So what I'd like to tell everybody about, if you haven't heard about it, the OpenSees Challenge 2012. At this year's OpenSees Days workshop, I'm going to give out 2 iPods. These iPods come out of my own, I buy them myself, so they're coming out of my own money. So anybody who submits the best OpenSees powered app to NESUB will win an iPod. And also the person who this year submits the best new code module, new element, material, solution algorithm, system of equation, they'll also receive an iPod. The winners will be judged by those attending the workshop. We're going to basically have a vote. I've already received a number of new code modules. I have not yet seen a new OpenSees powered app. Last year there was only 2 apps that got submitted, and one of those got disqualified, so there was basically only 1 app that got submitted. So this year none have been submitted, so anybody who writes anything, you're in with a shot to win an iPod. So if you're interested, all you have to do is submit it before the workshop, which this year will be August 15th and 16th. With that, I thank you, and I encourage you, based on what I'm presenting, to get your head out of the sand. Start using these amazing resources that we all have available to us. If we don't, as structural engineers, change how we do our simulation, as I say, we'll be like the ostrich with its head in the sand. So that's the end of the presentation. Let me quickly show you, before I start taking questions, on how we do some presentations. And for those of you interested in Kraken, I'm getting an email that Kraken is actually going to be re-enabled in the next 2 days. We have some more remaining allocation on the machine. So they're going to re-enable that for us, so we're going to be able to run these simulations in parallel if you want to on Kraken. So what I'm right now, if everybody can see, I'm actually in NESUB. I've actually logged into NESUB. I'm in sort of the My NESUB. And I'm quickly going to start the OpenSeesLab tool, just to show you what it looks like. So I say it's the OpenSeesLab tool. If you're not sure if it's the right one, just sort it by users. We got the most users, so it always pops up. And then you get a launch tool. You can launch the tool. So this is what the OpenSeesLab tool looks like when you launch it from your web browser. As I say, there's a number of tools within a tool. The one most people look at is basically the interpreter. So I have some examples here I could show you running. So that was example 2, but I'm just running it from my, let me run this one instead. So that's what example 1 does in the documentation. Now, as I said, if you have problems running your script, the really nice thing about this thing is you can hit the share button, and I could share this session, or you could share your session with me. You could share it with your advisor, showing them what's going on. And when you click share, it's basically going to ask you for who you want to share it with. So that's a unique thing about it. And the other nice thing is that you can have multiple things running at once. So you can, instead of, if you're running something and you want to leave it running, don't hit the X box. Just say, change the URL or go back to my NESUB. And here I have 2 things running. I'm going to show you the second one because it's the more up-to-date server. So to say, this tool here, this moment frame reliability analysis tool, it's coming. As I say, with one thing, the nice thing about it is you can see the changes, whether you're running sort of the mean value or 100 random samples. That's the roof displacement. I could look at, say, the base shear. How does the base shear change? It's kind of a simple Monte Carlo analysis. It's not very complicated. 100 simulations is obviously not enough. We'd probably need 1,000, maybe 10,000 simulations. This tool will be, it's in the clearing stages of being made available to everybody. But I quickly want to show you just submitting a parallel job. So I'm going to do the OpenSees parallel job submission. And this just sets up to the last default where I was running something. So as I say, the main script is, this is where I put the file. The important thing here is the file cannot go in your main directory. It has to go in a subdirectory off your main directory. My main directory is in home NESUB FMK. I've created a subdirectory examples, and in there is example 2.tickle. So that's the script you want to run. Then here's the different, when I click this pull down menu, I've got the different machines available to me. Right now, if you try Kraken, it's not going to work. Hansen or Steel are the 2 options to use. As I say, I was being told Kraken will be back available. And hopefully before I leave, June 14th, we'll have another option here, Ranger, which will allow you to run jobs on Ranger. So after you specify the resource you want to run, you've got the 2 options, OpenSeesMP or OpenSees SP, which application you want to run. And then finally, the number of processors. The number of processors available depends on the type of machine. Nice, Hansen, and Steel are limited in the number of processors you can run on. Kraken, it's up to, I think, 1,000 processes made available to you. And Ranger will have, I'm not sure what the limit they'll give us, but it'll be a large number of processes that would make it available to you. So the important thing here is to show you what happens when I run it. So let me change So this is what happens now when I run it. You click the simulate button, that submits the job. Now you don't see the results here. What it will come back and tell you is where your results will be. In this case, when I'm done, if I want to get the results, they're going to be in my /scratch OpenSeesMP job 00126 examples. That's where, if there's any output files from my script, that's where they'll be. And you will get an email from NEIS telling you when your job has been completed. So this might take, in this case, it'll take a couple of seconds to complete. But some jobs are taking, hours or days. You'll get an email from NEIS, when the job is completed, and then you can come back and check your email. Or you can actually come back to this location to actually get your data. So it's important to kind of jot down where the results are going to be put. The results are not going to be put back into your original directory for the simple reason that you might want to do multiple jobs. You might want to change the input file a little bit and do multiple runs while one job is running. This will allow you to do that if you put it in a separate location. And another important thing is we're putting it in the Scratch directory. We found that students typically generate an awful lot of output. They're doing an awful lot of stuff in their recorders. Scratch is, you've got to, basically it allows you to store an awful lot more data than in your home directory. So that's what the scratch is for. So that's the two reasons why your data is not going to be in the input directory that you started with. So with that, I will conclude the talk. And if anybody has any questions and they want to talk about it, one thing I should remind you, if you need to move data between the machines, there's an application called Synchronies. Allows you to move data between your local machine and NESUB. It's a real simple thing to use. Okay. So I'm done. So now I'll start taking any questions from anybody if they have any.